Okay, so here we are at long last with our video on volumes of revolution. This is going to be just a concept video, so we're going to do a really simple example, a couple of different ways to really sort of hammer home the idea, really get a really firm grasp of what's going on with this, because volumes of revolution are one of the things that I think give people the most trouble, that people are most sort of anxious about with a first year calculus course. I remember the first time I saw this, just not understanding it at all. It was very bewildering, and so people kind of see this as like the boogeyman of first year calculus. But it's really, if we understand what's going on, like so many other things in math, it's really not that bad. It's very straightforward if we actually know what we're doing here. So we're gonna really focus on the concepts. Speaking of the concepts, if you haven't seen the video on integration theory on Riemann sums, which is the one that went up just before this, might not be a bad idea to take a look at it, because we're going to be kind of generalizing the idea of what we did there into this case. This is, by the way, really cool. We would think, so if I take this banana slice kind of thing and I spin it around. I'm not going to attempt to draw this part. I'm going to have to do some 3D drawing in this, and my apologies in advance for that. Hopefully I can do it just well enough that you kind of get the idea of what's going on, but it will not be pretty. If I spin this thing around the y-axis, I'm going to get this three-dimensional shape, and you would think that I'd need, multivariable calculus or double integrals or something like that to find the volume of this, but I actually can do it with single variable tools, with just a single integral. And the way that we do that is by generalizing the notion of what we did in the integration theory video, where, just to briefly recap, I was trying to find the area under the bloody, again, so sorry, one of the kinks in this Procreate program that I'm using for this, that I have yet to work out, is why my pen just randomly turns into an eraser. I really have no idea. I'm not touching the screen at all. It just randomly switches over, and I have no clue how to stop this from happening. I've Googled it. I've sworn at the thing profusely. Nothing seems to help. Okay, so I have this graph of this function f, y is equal to f of x, and I want to find the area under the curve of this thing between 2 points. We thought about this very hand-wavily as taking a little line segment, which is going to have an infinitesimal width of dx and a height of f of x at any point, and adding these things up. And so we think about this as the sum, the infinite sum, going from a to b, x varying from a to b, and at each point we take the height of the function f of x and we multiply it by this infinitesimal width dx, and we're kind of taking this infinite sum of infinitesimally thin line segments, and they kind of pile up and give us the area under the curve, because the height of these things, the height of these sticks, varies as x goes from a to b. And that, again, I can't emphasize this enough, is not actually what's happening. It's a limit of Riemann sums, but that's how we think about it. And one of the reasons it's so helpful to think about that is because we're going to be now sort of generalizing this or extending this notion to the methods of washers and shells, where now, instead of thinking about this infinitesimal line segment, infinitesimally thin line segment going around, we're going to think, okay, at any point on this thing, I'm going to stop and take this infinitesimally thin kind of slice and look at the infinitesimal volume of the thing that I get when I rotate just this slice around here. And this thing is called a washer. I probably could have done this a little bit nicer, by the way. Let me just sort of kind of go back and stop there. Yeah, okay, I get a nice proper oval kind of thingy. It actually is a circle, though. We're going to see it from the top as well. This actually, the top view of this, the thing is a circle. Okay. And so I'm thinking about this now as spinning this infinitesimally thin stick thingy, which has an infinitesimal width of, actually in this case it's going to be a dy, spinning this around the axis of rotation, which is the y-axis in this case, and then I get this infinitesimally thin kind of washer thingy. We're calling it a washer. And these are the things that, as in this case, the y values are going to vary from here from 0 to 1. And by the way, I probably should have mentioned this already, or at the beginning, the way that I figured out the bounds of integration, when we do it on the y-axis as well as the x-axis, is going to go from 0 to 1. And there, as promised, is my thing switching to an eraser again on me. The reason we are going from 0 to 1 is that the points of intersection of these two functions are at 0, 0, and 1, 1. And we find that, I mean, it's obvious for these functions, but the way we find this is always at the beginning setting the two functions equal to one another, and getting and finding the points of intersection. Here x is going to be 0 and 1, so that's pretty easy to see. And I'm going to turn off my streamlining feature, which I use to get these nice curves, because it's kind of screwing up the writing. But all right, so as the y varies from, and it's an eraser again, as the y varies from 0 to 1, at each point I'm stopping and making this washer thingy, and then adding up all of these things. And these washers are kind of sweeping out this volume, just the way that line segment with the infinitesimal width dx swept out an area. I took sort of an infinite sum of line segments, and it gave me an area. Now I'm taking an infinite sum of these areas, gifting them with this infinitesimal width dy, and adding up, and I'm going to get a volume. And again, this is not actually what's happening. This is a way of thinking about it, which is very helpful. So how am I going to do this? Before, it wasn't that hard to put the integral together, right? I said, okay, what am I adding? I'm going from a to b, and I'm adding up these kind of infinitesimally thin rectangles. Each one has a height of f of x and an infinitesimal width of dx. Here I have to do a little bit more work, because now, well, I know where I'm adding from. I'm going from, in this case, 0 to 1 in the y direction, but I have to actually compute the area of the thing that I'm adding up. I know there's going to be a dy in there. That's my infinitesimal width y, infinitesimal in y, which is the width of this thing, which kind of drags it into the third dimension, the same way that the dx dragged that line segment into the second dimension. But now I have to multiply it by the area of this disk, or this washer thingy, which is actually two disks. It's one disk with then a little disk sort of hole punched in the middle of it. And so the way that I do this is I think about calculating the area of the bigger disk, the outside one, and then subtracting the area of the inner disk. And we know that the area of a circle is given by pi times r squared, where r is the radius. So I'm going to think about first the radius of the bigger circle. I'll call this capital, and I'll write it somewhere where you can actually see it. I'm going to call this capital R, and then we're also looking at the, maybe in dark blue, the inner radius, which is this guy, and that's going to be little r. And so the total area of this thing is going to be pi times big R squared minus pi times little r squared. And we can, of course, factor out the pi and make this big R squared minus little r squared. And that is what's going to go in here. But I actually have to figure out what these are. And I have to figure out what these are, these radii are, at a particular point y. So as I'm going from 0 up to 1, at every particular point y here, I have to stop and say, okay, what is... I'll do the same colors. What is the little radius, little r, and what is the big radius, capital R here? And the key to doing this is noticing that the capital R, this orange radius capital R, is the x-coordinate of the point on the function y is equal to x squared that this y value here determines, and the inner radius, the little r, so this is little r, and then this is big R. The little r is the x-coordinate of the point determined on the line by this y value on the line y is equal to x. So the little r is easy enough to find. The little r is just going to be the y value of the point, because y is equal to x there. But this big R, well, this is the x-coordinate of a point on the line y is equal to x squared, and so that's going to give me x is equal to the square root of y. And this is important. I have to solve for x in terms of y. By the way, I can take the positive square root because this is a radius. I want a positive radius. But the idea is that I can actually get a value for x at that y point. That's not always possible, and that's why we're gonna look at the shell method next. But for this one, I can actually figure out what the radius is. It is root y. So let me get rid of this arrow thing here to give myself some space, and we're gonna put in these radii. So I have of course the dy, the infinitesimal width that we're multiplying by, and then I'm going to take, after I get my pen back yet again, I'm going to take root y and plug it in for capital R here, and then just y and plug it in for R there. And I'll do that in a nicer color. I don't like this blue. I'm going to put in here, and I'm gonna factor out the pi. This is an integral, so it's nice and linear, so I can bring the pi out here and put in root y minus y dy, and that's the integral. That is actually this thing. Oh, sorry, and I have to square them. So I'd square, we can't forget that. There are little things, by the way, in these problems that cost you marks. The one that probably would cost me marks if I was doing this is forgetting to square them. I always do stuff like that. 0 to 1, you guys won't, of course. You're all going to get all the marks on these problems. It's going to be pi times integral from 0 to 1, or pi times the integral from 0 to 1 of y minus now y squared dy. That's the integral that's going to give us this volume. And so again, we're thinking about this in bits, right? We're piecing it together bit by bit, saying, okay, what do I need? I need my infinitesimal width dy. And then I need to have the correct bounds of integration. What's changing? What is varying? Always ask yourself in integration problems, what is changing? Well, it's the y, and it's changing from 0 to 1. I figured that out at the beginning. It's going there. And then I have to think, okay, what am I multiplying this infinitesimal width dy by? Well, it's going to be the area of this washer thing, which I can just use my circle area formulae over here to figure out. It ends up being y minus y squared. And so this process of piecing the integral together by saying, okay, what is the slice? First step is, what am I slicing, right? What is the cross section that I get? Here it's a disk. And then how do I figure out at this particular point y what the area of that disk is going to be? Can I do that? I might have to use a different method, but generally I'm thinking, how do I at this point y figure out the area? And then just where is it varying from? What is the range that I'm picking the y's from? Here I'm picking the y's in between 0 and 1, and at any particular point I can find the area of the slice multiplied by the dy, add them all up, and I get the volume. And that's the disk method. But as I mentioned, so down here we had to solve for x in terms of y in order to find the outer radius of this thing. So, and we're not always going to be able to do that. So in the next video, or the second part of this video, which I'm going to pause it now and split it up. In the next part, we're going to be doing the shell method, which is going to be integrating with respect to x, and that will give us an option. So if we can't solve for x in terms of y, at least explicitly, we can do shells instead. And also, it's just cool. It's always cool to have several ways to do the same thing, especially because if you have two ways of computing the same quantity in math, you can always check that you haven't made a mistake by doing both of them. It's great practice. And also, if you get two different results, two different numbers, you've done something wrong, and you go back and check your work. So that'll be next up.